Hello, my name is Gary Pocock and this is my Week 7 reflection for the Physics Modelling Instruction course. This week I'm going to reflect on David's post on Edmodo discussing the lack of conceptual explanations in physics textbooks for the different field configurations we find for thin rods and for charged planes. When I read David's post, I went back and looked at all the textbooks, and he's absolutely right. They all rely on entirely on mathematics. Some give some conceptual explanations, but not a lot, and this struck me as quite remarkable. So that set me off on a little search to see if I could have come up with some conceptual explanations. So just to start with, I'd just like to mention a quote that I've mentioned before, and this is from a paper by Roche, which looks like this, and it's from 1989, so he's certainly feeling the same problem way back then, and the quote is that verbal explanations are neglected, or at least have not been developed to the same extent as mathematical and experimental presentations in physics. And that is certainly the case when it comes to field derivations for thin rods and planes of charge. So it is also definitely true that Gauss's law does not provide us with any conceptual insight into these field structures. However, looking at the Coulomb's law derivations, that gave me a few clues as to how a conceptual explanation might go, and that's what I'm going to try and work through. So I'm going to draw on material from a couple of different books, Charvet and Sherwood, who go out of their way to try and provide some clarity in their explanations, and I'm also going to rely on a couple of diagrams from Tipler's physics book. I should also mention Knight's book, which also is quite good in trying to provide some explanation, but none of them go far enough, I think. Now, because it's such a big job, I'm just going to focus on a single thin rod and a single thin plane rather than looking at pairs of them. I'm going to suggest that the hard work conceptually is done by focusing on these single rods and single planes, and when you move to a pair, things are then not quite so difficult, I think. Alright, so let's start off with a uniformly charged thin rod, and note my terminology. I really think it's a good idea to use the word rod rather than line of charge, just to emphasize that it really is a 3D object that we're talking about here. So first let's consider the direction of a field around a thin rod, and there's two possible ways of approaching this. First of all, we can just use symmetry, and this is the approach that Charvet and Sherwood use. And they point out that we have cylindrical symmetry because we have a thin rod, and so these diagrams are from Charvet and Sherwood. This is a cross-section here of the thin rod, and we get this spherical symmetry when we look at the cross-section. Note they've also slipped in some indications that the field is getting weaker, but that's a magnitude question which hasn't been addressed yet. And then we have a nice 3D diagram, again suggesting by symmetry that the field is radial, at least around near the center of the rod, and we get fringe effects at the end. Second approach is one suggested by Matt a couple of weeks ago, and that is to use the electric field software and gradually build up our thin rod of charge as a series of point charges, and we can see progressively how the field gradually becomes more and more, the field lines become more and more parallel near the center of the field the more charges we include. And that's a very nice approach. But I will mention at this point that one difficulty with any of these visual approaches is that there is no way that we can indicate the magnitude of the field near the actual charges themselves. In particular, we can't indicate whether the field is going to infinity or whether it's finite. All we know is from these diagrams that it's large near the charge and gradually thinning out the further we get. And I think it would be a good idea if textbooks used shading as well as field lines and field vectors to indicate the strength of the field, just to reinforce the fact that just to reinforce the changing magnitude of the field. And that's particularly the case with this kind of field here, because students are also used to seeing fields for parallel plates of charge, and as soon as they see parallel lines, they're going to be prone to thinking, we've got a uniform field, uniform in magnitude. And we certainly don't have that in the case of a thin rod, as we will now see. Alright, so how do we analyze the magnitude of the field around a thin rod? Well, focusing on the mid-plane of the rod to maximize our use of symmetry. And this diagram is taken from Charbet and Sherwood, and the strategy is to take symmetrical charges around the midline. And then we can see that the y components cancel out, and the net field due to these two charges is simply the sum of the x components. And we have to imagine the total field here is the sum of all the pairs along the rod. Okay, so what tendencies can we see conceptually? Well, we can imagine that if we have a finite rod and we move far away from the rod, then the rod is going to behave like a point charge. So we would expect an inverse square relationship at a reasonable distance from the rod. So the next question is, what happens as we get closer and closer to the rod? And here we see we have two effects that are working in opposite directions. So these arrows I've superimposed on the diagram. As we get closer to the rod, the size of the field gets bigger because the distance gets smaller. However, because of the increased angle, the x component contribution is a smaller percentage of the overall size of the field. So we've got these two opposing factors. The field itself is getting larger, but the x component is getting smaller. So it's not clear which one's going to win, so to speak. But I think you can make a plausible argument that as you get closer and closer to the center of the rod, you're going to get closer and closer to an actual point charge on the rod. So I think it's reasonable to expect the field to go off to infinity, just like it does when you get close to a point charge. And indeed it does. However, it doesn't go to infinity as 1 on r squared. But that's a mathematical thing. All we need to establish conceptually, I think, is that it's not unreasonable to conclude that the field will tend to infinity as you get closer and closer to the rod itself. And this diagram I've taken from Tipler, which I think gives a nice summary of the relationships. So the blue line is the 1 on r relationship for an infinite rod. The green line is the 1 on r squared relationship for a point charge. And here we have a finite rod which behaves like a point charge, behaves like an infinite rod for small r and behaves like a point charge for large r. Alright, so there is our thin rod field explained in a reasonable conceptual way, I think. And that point I've already made. There's no way in our diagrams we can indicate that the field goes to infinity as we get close to the rod. And this is a key point when we get to the thin plane. Alright, so how do we deal with the thin plane? Now here the Coulomb's law approach provides a clue. You don't analyze the thin plane straight off. You approach it via analysis of a thin ring. And then you construct a disk out of a series of concentric thin rings, and then you move to the infinite plane. So let's see how that works. So starting with a thin ring, direction is, again, we're focusing on the z-axis, the central axis of the thin ring, and working out the field there. So direction is clearly going to be radial. What about the magnitude? Okay, once again, we would expect a roughly inverse square relationship as we move far away from the ring. And once again, we get these opposing effects as you move close to the ring. The size of the field contributing for individual point of charge will increase, but the x component of that field will decrease. So again, the question is, which effect is going to win? Well, the interesting thing in this case is that if we go right to the center of the ring, and there is no charges here, unlike the thin rod situation. So symmetry tells us that the field in the center of the ring is going to be 0. So we've got an inverse square relationship for large values of z, but 0 at the center. So that tells us that there must be some peak somewhere in between. And so here we get a plausible construction of the field for a thin ring. It must go through 0. So what happens if you change the radius of the ring? Bigger radius, peaks get small. Smaller radius, peak gets larger and gets closer and closer to the center of the ring. So if you combine these together with a series of concentric rings, which I've done on a spreadsheet. So this is, I've started with a ring of radius 1 millimeter and I've gone out to 1 centimeter with 100 subintervals in between and added all the fields together with a total charge of 1 nanocoulomb, same charge as was on the thin ring before, but this time the total charge is distributed over all the rings. And what you see is the peak is getting closer and closer to the 0 point, but it is not shooting off to infinity. And that's the clue, that's the key point. The maximum field for this disk is going to be a finite number. And this all centers around the fact that it has to be 0 in the center here. So I'm imagining this disk being constructed by concentric rings filled in from the outside going in, and we just leave that little hole in the center all the time. And that's why the field goes to 0. And there's a nice diagram summarizing the situation. The infinite plane is just when you make the rings bigger and bigger and bigger, and this will build up this curved part down here and boost it up to a horizontal line. A simulation would be ideal here to show this effect. So here's the key difference. I've circled it in red there. For a disk, the maximum field is finite, right up against the disk. And this is something that none of the textbooks discuss, and it's quite in contrast to what happens with a charged rod, thin rod. And just to hammer home the point of how difficult and how easy it is to get confused about these situations, here are two diagrams from Charvet and Sherwood. One's a thin rod, one's an end-on view of the disk. You can look at those and it's not surprising that students can get confused. Alright, so that's a very quick tour of my thinking in the past week on how we can conceptually explain the difference in fields between a disk and a charged rod.